In this video, we're going to talk about the possibilities of three planes in an R3 space. Alright, first, we need to know about some prerequisites. We need to know about what is a normal or a normal vector, and we also need to know about scalar multiples. So let's start. A normal is a vector that is perpendicular to the plane, meaning the angle from the normal to the plane is 90 degrees. We can check if they are perpendicular by using dot product. If the dot product of the two vectors equals to 0, then they are perpendicular. If the dot product does not equal to 0, then they are not perpendicular. Here's an example. Here we have a normal and a vector that lies on the plane. So let's apply dot product to these vectors to see if they are perpendicular to each other. 1, 2, 2, dot product 2, negative 1, 0 equals to 2 minus 2 plus 0. So that equals to 0. Therefore, they are perpendicular to each other. So we're going to see when three planes exist in a three-dimensional space. A 3D space has an x-axis, a y-axis, and a z-axis. We also call this space R3. Here we have a flowchart that shows all the possible outcomes of three planes in an R3 space. We have three main scenarios. We can have all three planes parallel to each other, or they could all be intersecting with each other, or the two planes can be parallel and coincident with one plane intersecting. So how are we going to distinguish whether the three planes are one of the scenarios or the other? We can start by comparing the normals from the scalar equations of each plane. As we know, if all the planes are parallel, then their normals will also be the same. For example, we have three planes, pi 1, pi 2, and pi 3. For these equations, we know that n1 equals to 4, negative 2, and 6, n2 is 6, negative 3, and 9, and n3 is negative 10, 5, and negative 15. Simplifying the normals of all three planes would be 2, negative 1, and 3. Hence, these planes are all parallel. Now, we want to find if the planes are either distinct, coincident, or two coincidents with one distinct. We can find this by comparing the d values of the equation. We know the normals are parallel from comparing the normal ratio. We next compare the ratio of the d values. If the ratios are different, then they are distinct. If the ratios are the same, then they are coincident. If two ratios are the same and the other is different, then they are coincident and one distinct. For example, let's use the previous planes. The normals are 4, negative 2, and 6, 6, negative 3, and 9, and negative 10, 5, and negative 15, which they all share the same normal of 2, negative 1, and 3 when simplified. Now we will compare the values of d based on their ratios. Pi 1 over pi 2 has a ratio of negative 2 over 5. However, 35 over 20 has a ratio of 7 over 4. The ratios show different values. Hence, d1 does not equal to kd2, where k represents the scalar multiple of d. Now compare pi 2 over pi 3, which has a ratio of negative 5 over 3, but 20 over negative 50 has a ratio of negative 2 over 5. Therefore, d1 does not equal to kd2 and neither equals to kd3. This shows the planes are parallel and distinct. Next, we want to find when does the three planes intersect with each other. When comparing the normals of each plane, the normals will not be the same, meaning they're not parallel. To identify whether the planes intersect pairwise, or if the planes intersect in a line, or if the planes intersect at a point, we will use the volume test. The volume test is to find whether the normals are coplanar or not. This is the formula. n1 dot product of n2 cross product of n3. If the volume test equals to 0, the normals are coplanar, and the planes intersect either in a line or pairwise. If the volume test does not equal to 0, the normals are not coplanar and the planes intersect at a single point. If the planes are coplanar, we will then solve the system algebraically to determine if there is a solution. This is work with pairs of equations to eliminate the variables. If the system has no solution, these planes intersect in pairs, whereas this equation is true with all values of y and z. Therefore, these three planes intersect in a line. Here's an example of the whole process if the volume test equals to 0. We have three planes, and we have the normals. We can already see none of the normals are parallel. Therefore, none of the planes are parallel. We next want to know if the normals are coplanar. We'll use the volume test, starting with cross product of n2 and n3, which equals to 17, -17, and -51, and dot product that with n1 equals to 0. So with volume test equals to 0, this means they are coplanar. Next, we must solve the system. If it is a true statement, then the planes intersect in a line. Or if it's a false statement, then the planes intersect pairwise. Let's work with pairs of equations. We want to eliminate one of the variables. We'll eliminate x. Pi1 plus pi2 equals to -12y plus 4z equals to 16. We'll call this equation 4. Then pi2 times -8 plus pi3 equals to 51y minus 17z equals to -68. We'll call this equation 5. Now we eliminate y from equations 4 and 5. Pi4 times 17 plus pi5 times 4 makes both sides equal to 0. The system is true, thus the planes intersect in a line. Next, we determine the parametric equation of the line. First, we'll let z be the parameter, letting z equal to t. Then we substitute t into equation 7, hence finding y equals to 1/3 t minus 4/3. Lastly, what if the volume test does not equal to 0? The normals are not coplanar and the planes intersect in a single point. We will work with pairs of the equations to eliminate the variables and solve the unknowns of x, y, and z. With volumes x, y, and z, we will know the point of intersection. For the last situation of three planes in R3 is when two parallel planes are intersecting with one plane. This situation is basically a combination of parallel planes and intersecting planes. The parallel planes could be distinct or coincident. For this situation, two normals are the same and one is different. The normals of two parallel planes with one plane intersecting has normal 1 equal to normal 2, but not equal to normal 3. Then, to differentiate whether the planes are distinct or coincident, is to check the d values of the plane. If d1 does not equal to d2, then the planes are distinct. If d1 equals to d2, then the planes are coincident. And this is how you find the possible relations between three planes in an R3 space. Thanks for watching.